Uh, okay, so ready to go? Just before we start on the interrupts, I just wanted to say a couple of words about the homework because there seems to be some confusion about what is it we're doing. Let's quickly the page here. So just what is the homework about? The homework is about building a tiny, very primitive memory allocator, which is conceptually similar to what x86 is doing. So it just allocates a free page, right? And then using it to construct a page table, again, in a manner very similar to how x86 is doing it. And in fact, I said, okay, you can borrow the code if you like, right? So, but it looks like the whole idea of virtualization of memory and stuff like that gets a little tricky if you've never done it before, right? So let me draw a picture for you, or figure. So imagine this is your physical memory, right? And I said, okay, let's just only handle 32 megabytes of physical memory, right? It's from 0, this is physical, to 32 megabytes. So we kind of know that the area below the first megabyte is a little special. So like some bias. When I say bias, I mean mostly it's I/O space, meaning that if you start writing into this memory, the hardware will pick up the input and will reflect maybe something on a screen, right? And so what we did is that the way we compiled everything in the homework 3, right? So we said we're going to use grub and everything, which skips parts of the boot loading. But what it does for us is that it loads the kernel into this area, right? This is where our kernel, this primitive hello world kernel sits, right? So starting at the first megabyte, right? Agree with this? So the homework says, okay, make sure that you understand where the end of the kernel is. So add this and symbol here, right? And map all the memory starting from the next page. So there is like a tiny roundup here, right? Okay, I'm not saying map, but like this is the physical memory which your allocator will track, right? Agree with this? Everyone, right? The question is like, how are you going to track those pages, right? And x86 says, okay, so let me first show you what x86 is doing. x86 says we're going to have a head pointer here inside the kernel in a data section. And the head will point to the first available page, like this one. Maybe let me Control Z here. Like this, there will be a pointer to the next page and so on, right? That's okay. That's one way to design it. Later on in class, I will explain why this design has limitations, right? And so we're doing something different, right? A couple of limitations here is that in order to even write into this page, like if you want to initialize this next element, do some memory write here, you need these pages to be mapped, right? To begin with. Agree with this? Okay, cool. So we're not going to do this. So let me just undo the blue part. And instead, let's say we will switch to green here and say, okay, the assignment says, let's manage the memory in a slightly different manner. So we will allocate an array here. This array will describe each physical page in a system, right? So if I magnify it and like do a larger picture, conceptually, it's an array of elements. Each element is I call it a type page, right? So you can call it anything, right? But that's the way. And it's allocated obviously in the data section because it's a global variable or BSS, whatever you like, right? And so it also comes with a metadata element here. And that's an element which says, okay, I'll point to the first element of the linked list. And then you say, look, in practice, and I draw it like, let's draw it out of order for the sake of it. It keeps track of available pages as a list, right? That's clear? Yeah. Also, there is the following convention that each element of the array specifically describes one page. So for example, this element 0 describes this page 0, right? I don't know, let's say 55 describes page, let's say this is the page 55, right? It corresponds. So essentially, when you say something like page alloc, your goal is to say, like, I really want a page with ppn, whatever was next on the list. So in this specific example, page 0 was on the list. So you will get a page, you will get an address 0, right? But imagine at some point you do a couple of other allocations and you say page alloc, and at some point you get internally, your code will understand that, okay, look, the moment we get to the next, which is 55, since we're allocating this element from the array, it means that the page with ppn 55 is available. So the address will be something like x55 000, like this, probably, right? Correct? Agree with this?
Yes.
This way, we keep track of all available physical memory in the system, right? And in our case, I say we only have to track up to 32 megabytes, right? We can change this constant. We can track anything, right? So cool, right? And then the second part of the homework says, okay, map all the memory from 0 to 32. So create an address space, meaning that you will construct a page table with multiple levels, obviously, which will map the physical memory and virtual memory one-to-one. So your address space will be kind of like this, right? So page 0 in virtual will be mapped to page 0 in physical, right? And similar page 55, which is here, will be mapped to physical page 55, right? Okay, easy. So how we do that, right? So obviously, in order to even construct a page table, because we know that's your pointer, the page table, you need this page, right? To essentially to keep the page table directory. So you get it from the allocator. So this your first invocation of the page alloc function will return you some page, right? Okay, cool. What if it returns happens to return again page 55? So this physical page 55. That might lead to the following unfortunate case. It might lead to the case that when this page, if you do a write into this page, right, trying to create a mapping, right, connect maybe page table directory and this page table 1, for example. So you do a write here, might cause a page fault. Why is that, right? Because we're currently running on some other page table, the one which you created in homework 3, right? And this page table, let's make it orange, right? Let's call it, and it literally just 3 pages, right? So page table directory, page table 1, and page table 2. Because I forget exactly what I was asking in the homework. Did we map 2 megabytes or we map more? 8? Okay, so it maps everything from 0 to, let's say, 8 megabytes, right? So if you get a page, one of those pages from page alloc, you'll be just totally fine. The write will go through, right? But if suddenly your page, which you're getting from it, from the allocator, is outside of this mapped region, obviously this entry in a page table is not present, because it has to lead to like some other page here, page table here, right? Which doesn't exist, right? And it causes a page fault. That's why I'm saying, okay, be careful with this. Make sure that you maybe originally, instead of adding all pages, all 32 megabytes of physical memory to the free list, just add everything up to 8 megabyte. This guarantees that no matter which page you get from the memory allocator will be mapped by your current page table, right? And then do it in 2 steps. So first construct this, like add everything up to 8 megabyte, construct this page table, then switch to it, and then add the other pages, right? That's the correct execution of this homework. And it's exactly what x6 is doing, right? If you carefully see, like, remember, there's this function which initializes the memory allocator, but it only initializes with pages up to 4 MB because x6 maps only 4 MB, right? Is that clear? Or is it too complicated at this point even? Any questions?
Do we need to implement the page fault like when we
No page fault.
Just if there's no, just allocate.
No, just you have to construct everything carefully to avoid the page fault. Yeah, page fault is a viable strategy. You can implement it, but typically people don't do it just at this stage.
What really confused me about this homework was if you just use page alloc directly and don't have it already, if you use the address that's allocated from that, it still results in.
Say this again. So, like, if the page is outside of 8 MB region or whatever the region your current page table, this one, like let's say boot time page table.
Right. So if it's not already mapped to in the page table, but you still use page alloc.
Yeah, then it can result in a page fault.
So that really sent me for a loop. What then would be the point of page alloc?
I see. Okay. So what you're saying is that, okay, let me explain it through like two different kind of ways, right? In two different ways. So first one, do you understand my kind of line here where I say, look, if you do it in two steps, first initialize the page alloc with pages below 8 MB. That will prevent you from getting a page fault, right? Then later on, you map all 32 MB, right? Which at this point guarantees that your kernel is smart enough to make sure that any page in a system will be mapped one-to-one with this page table, right? So when you say, I want a system which handles 32 MB of physical memory, and you achieve a guarantee that everything will be mapped, so you will never get a page fault again, right? Do you agree with this? Okay, cool. So that's way number one. And then way number two, so if we all agree that we understand why this is done, because this guarantees that no matter which page you get from the allocator later on, let me maybe switch to, like, for example, this page, and it returns you a page with a physical page number, let's say 88. You can freely, the kernel on this page table, on the blue page table, can always access it, right? It's convenient and it's practical, right? There are cases where this is not really necessary. For example, you say, look, I can imagine later on, for whatever reason, you say, and I actually have 1 TB of physical memory. It's like, there are machines in Emulab which have 1 TB. We were using them for experimentation because we have data sets and you say, look, do it really, like, if the kernel itself never accesses this page, for example, it never writes, even if it allocates from a page alloc, it will not access it. Maybe it will map it into the user address space, but it will never access it again because it gives it to the user, right? And you can ask a question, but is it realistic that the kernel will never access this page? Because even if you give a page to the user, you probably have to initialize it with zeros to prevent any kind of data leakage attack, right? So you can temporarily map it and then map it immediately, just because you say, I don't foresee accessing this page frequently. I don't have to keep it on my page table. And then it will, of course, like, save you a little bit of levels, those pages which are required to even map this terabyte page, right? So terabyte address space will require four level of those page tables, right? So this is really done in practice. So not all physical memory has to be mapped in a kernel, but we do it this way for simplicity. Does this help answer your question? Okay, cool. Yeah, obviously. But I wanted everyone to kind of, you asked a question online and I realized that maybe it's worth touching on this in class. You mean our testing code?
Yeah, like, well, so and then XP6,
So there is a testing code in x86 which does it as well. I honestly, I'm not aware. Yeah. x86, and I can, yeah, that's a good, yeah, yeah. Correct. Okay, there's a couple of things here. First of all, x86 doesn't support page faults whatsoever. Like they carefully construct the address spaces in such a manner that they will never get a page fault. User can get a page fault. I should probably take it back. So maybe they will terminate the process if user accesses the address. Yeah, they will obviously, right? And we should take a look even today how they handle a page fault, right? What x86 is doing, let me just quickly. Yeah. Yeah. Let's quickly take a look at it. So, sorry, not this lecture. So x86 does the following. So they first initialize the allocator. They first initialize the allocator in this. They have some kind of a boot time page table, right? Remember, it's a 4 megabyte page table, which has only 2 entries, right? And it maps virtual memory from 2 gigabytes to 2 gigabytes plus 4 megabytes, right? So all of these physical pages started from the end until the end of the 4th megabyte here are mapped, right? And they invoke a function. Let me show you the name of this function, right? So when you, hold on, that's not it. This is, when they boot into main, they invoke this function kinit1. Kinit1 says, okay, please initialize the memory allocator starting from the end up until 4th megabyte, right? And so those pages which I was talking about, these ones, are added to the allocator, right? They guarantee that when you write into those pages, it's mapped, they are mapped by the boot time page table, right? So this doesn't cause a page fault, right? It adds enough pages because we counted them in a homework and it was something like, what is it? 700, I forgot exactly the answer, 740 or something, right? Enough to construct a different page table, which is conceptually similar to what I am asking you to do in this homework, right? And at the very end of this main function, and maybe I have to switch to, I don't know if I have it on a slide. At the very end of this boot sequence, like, so if we see here, I go into the main, they said, we will finish in this, like, this is kinit1, right here, right? And then they do all the initialization, and then they switch to that new page table. And after that, they say, by the way, now add all the way, map all physical memory starting from the 2 gigabytes plus 4 megabytes to the end of the pistol. That's the max amount of physical memory which they handle. So that's the trick which I'm asking you to do as well. I don't know, I wasn't exactly sure what you were asking, but they construct it like similar to how I asked you to do that in homework. They construct a new page table and they switch to that new page table because the boot time page table was covering only a small fraction of the address space. Does this help?
Yeah, I just I was wondering why, like they shut off aging, so I
But wait, where do you think they start off paging? Paging is all on here, like all the time. KB Malloc. Okay, let's take a look. Yeah, so this is how I read the source code. It's not ideal, so probably Microsoft Visual Studio will construct a cross-reference, right? GitLab will do that for you as well, right? But I'm like, okay, cool. So this function essentially says set up KVM, so it creates a new page table directory, right? Which maps everything in this map range, the entire address space which they want to handle, right? With these 4 regions, right? And they switch to this switch KVM. Switch KVM, essentially what it does, it loads something into CR3. So it just switches the root of the page table, but it does not disable paging. Paging is always on. Is that what you were? No, so if you carefully look, so set up KVM doesn't turn off paging, right? And it's allocates a new page table directory in this line, right? Then it does like initialize it with 0. And then it says, okay, I have a map of the address space with 4 entries, and I will use map pages to essentially map each region in this map, right? So it's 4 regions. It's very similar to what I asked you to do in the homework. Is that just that I say map everything? No worries about regions like IO spacing. So again, I appreciate the question. So and it's good that I really appreciate the fact that you cross-checking your understanding from the lectures with the source code. That's what I'm asking you to do in this class, right? So that's the way to succeed, right? So I will tell you an anecdote. Maybe I told it already. So okay, sorry. I had a female student in maybe like 5 years ago at UC Irvine. At the end of the class, at the end of the semester or quarter at UC Irvine, I think she was the top student in the class, and I wanted to hire her. Like, I reached out to her to make an offer, asking, can you join my team? And because you did so well in this class. She said, okay, I don't want to, I want to do grad school, not with you, so I'm going to leave. Or no, she went for a job, like she graduated, went for a job, right? But as part of that, my making an offer, I asked her what's the secret? Why is that you did so well, right? And she said, okay, I was really like reading the source code. You told me to read and I read it, right? And that was the trick, right? So that's really the trick in this class. So despite the fact that I teach a lot of lectures, there are videos, quizzes, the real deal is to read the source code. If you read the source code, it's not that hard, I promise. It's hard for the first 2 days, and then it becomes easy, right? And it's the same with any other code base. And you will see that if you want to succeed, you have to read this source in many, many cases. Okay, so okay, good. So my whatever deviation is over. So yeah.
Yeah. So you said we can map more like 1 gigabyte, 2 gigabyte should also be fine, right?
You can map more. What do you mean?
I mean, here you said we map only 8 megabyte or 32 megabyte. We can map more, right?
Yeah.
2 gigabyte.
Yeah. At some point, you will run into problems. It's a good kind of quiz question. I will ask you on it. Yeah. This week. So what do you think? What's the maximum amount of physical memory this design can support? And that will be, you will have to answer. But technically speaking, you will not run into problems for a while, and then eventually will run into problems. So you can simply change this constant to be something like 256. The question like, can you go up to 4 GBs? And you will tell me yes or no and how. Right? Good question.
My question is that we only do mapping here. Actually, this seems to be fake to me because right, we only do map. We don't do the actual allocate. It's really seems fake to me.
What do you mean? Like, okay, yeah. Okay.
Yeah, you can map any pages, but actually you only map on a page table. Actually, you do not allocate. Right?
That was my question too.
Correct.
Yeah.
Correct. So, and that's probably why your question triggered this discussion. So I agree. So it's a little kind of like twists your mind a little. So why is it you're doing this even to,
Yeah,
if you don't really, you say you map the address space, right? So everything is mapped. So meaning if you do a move into any of those addresses, this or this, it will go through, right?
yeah,
But the question, do you have to use those pages in any way or not? And upfront you don't, right? So you say, look,
yeah,
I only use a fraction. So maybe I will use one page for the page table directory, this one. And then to map 32, it's 32 divided by 4. So you will have to use 8 of this, right? So the total will be 9 pages, right? You will literally call page aleph 9 times, right? In this homework, I assume, right? But the question, like, why do you map everything? So can you tell me? So why? Or what's the kind of the gist? Why does it make sense? Why does it make sense?
I don't answer, I'm not going to claim to be that smart, but, to kind of put us back into context, is this page out meant to be used by both the user and the kernel? I think that would help.
Mostly by the kernel, but user can also use it if the user says sbrk, give me a page. So then we will go into this page allocator because we can only give a page which we have on the allocator, right? If we already allocated this first 8 pages, we need to make sure that we will never give it to the user because they will be able to overwrite our like page table, right? Page table directory. So let me give you an intuition, right? So the next homework, or maybe one after that, will ask you to essentially load an ELF file. So essentially our user part of the address space will start at some boundary, let's say 8 megabyte, right? And I will say, okay, please load an ELF file here, right? And you will be inside the kernel, you will be actually copying into those pages the loadable sections of the ELF, right? You will touch them. So this original allocator kind of like keeps track physical resources, right? So you say, I have that many physical pages. If I need one, I'll get one. And then this is back to this story. If you don't have to access this page, you don't need it. You don't have to have it mapped. But if you suddenly have to copy into this page, like do part of the ELF file, then it's better to have, you better have it mapped. Otherwise a page, right? And you can do it lazily. You don't have to map everything up front. You can handle page faults. You can, every time you access a page, you can check and map it at that moment in time and then unmap it, right? So it's all legit design choices. For simplicity, I say, let's map everything up front. And partially just to test your implementation of the code, right? Does it answer the question, right? Yeah. Okay, good. So any other questions on the homework? I mean, people who haven't started yet, they can watch the video and probably it will become clear. Okay, good. Okay, so then back to the lecture. So save this just in case. Okay, our plan for today is to I optimistically hope to finish, but we're not going to finish probably at this time. But move on with the interrupts. So we already know how interrupt is handled when you don't have to switch privilege levels. We, by the way, know what privilege levels are, which is great because suddenly, you know, like everything makes sense. We know how isolation works on x86. The combination of segmentation, which keeps track of privilege level, and paging, which says, okay, whether you can access the page or not in the page table. And we know how the page table, how privilege level transition happens, you know, like when you go through the interrupt table, you pick a interrupt descriptor from the interrupt descriptor table that will have a new privilege level for you, right? And you will suddenly switch from 3 to 0, for example. And we started looking at the interrupt descriptor table last time. On Intel, it has the max of 256 entries. And I was saying that entries from 0 to 32 are special. They are reserved by Intel. So Intel says I'm going to use them in one way or another. And those are actually synchronous. Most of them are synchronous exceptions, right? So essentially like division by 0, our wonderful page fault, protection violation, stuff like that, right? So we got it. And so our plan today is to move on and see, first of all, how we handle an interrupt from a device, which number is that actually, and actual C code, C and assembly code in the kernel, which implements an interrupt handler, right? That's the plan. Okay, cool. So we like have a decent like idea of this table. As I was saying, entries are 0 to 31 are reserved by Intel. For example, 14 is always a page fault. Entries 32 to 255 can be configured by software. So essentially, when an operating system boots, it can negotiate with the hardware which device is assigned which interrupt. Often, in most cases, entries 32 to 47 are more or less fixed, and they fixed for like a specific subset of device interrupts. One of them is a timer. So timer is actually entry 32, and those are historically called IRQs. What is that? Interrupt request. What is IRQ? I don't remember myself anymore. But when you see a word IRQ, you know that essentially it talks about this, what is that, 16 interrupts, which start from entry 32, right? And I was mentioning earlier that interrupts also provide a way to implement system calls, because the nature of it is that you can transition from ring 3 into ring 0. So kind of call a function in the kernel, right? And it's all protected, meaning that you cannot really, and we'll see how, you cannot really like randomly call an address in the kernel. You can only say, in your user code, you can say int, for example, OX80, and then it will immediately trigger a transition and will go through the interrupt descriptor table. And this is where the operating system will put a pointer to the handler of vector of interrupt 80, right? So, and this is what we'll cover today. Okay, cool. So Linux uses X80, which is DEC 128, and x86 uses interrupt X40, which is 64 for implementing the system call. And today there are faster ways to enter the kernel, but they're a little bit more cumbersome. So let's just stick to the interrupts for a second. Okay, cool. So a note on disabling interrupts, right? So there are cases where you write the code, and it will become a little bit clear in a couple of weeks when we're going to talk about concurrency, essentially how you ensure that a fraction of your code essentially executes without interference with any other part of the system, right? And you say, look, like imagine you're trying to add something on a linked list, like even like this, the same page alloc, right? Maybe you're allocating a new page from the memory allocator. You have something like a head here. You are in the middle of an interrupt. You say, look, I'm clearly will take this page off the list. I will look at this next element and will update the head pointer to point to this next page, right? And suddenly another interrupt occurs. And it also wants to allocate a page, right? At this point, you may end up, like they will also look at the head. They will also do this, right? And you will end up with a linked list which loses one element, or like otherwise or vice versa, you allocate this page twice, right? And we'll talk about concurrency and everything, but just a heads up, there are cases where you say, look, you cannot handle yet another interrupt, right? And on Intel, you can disable interrupts by changing a bit, interrupt flag bit in the eFlags register, right? And there is a special instruction which does it, which is CLI, clear interrupt, right? But you can actually like reload the eFlags register by pushing back into the popping from, for example, you can save interrupt register eFlags on the stack and then load it back into the eFlags register, right? So it also will disable the interrupts. Okay, cool, that's nice. So you say, look, I got it. I can disable interrupts, but obviously there are some exceptions from this rule. Exception number one is that synchronous interrupts or exceptions, I mean, because a synchronous interrupt is called an exception, cannot be disabled, right? As we discussed before, it doesn't make sense to disable a page fault, because really, if you're trying to access a page which is not mapped, you really better map it, right? Or do something, or kill the process, or something like that, right? So this logic is clear, right? Right? So synchronous. So if your code has something like an int X40, which tries to invoke a system call in x86, you cannot disable this instruction. So it will always trigger a transition through the interrupt descriptor table, right? No matter no matter the state of the E flags register, right? Okay, but there is also yet another exception for this rule. There is one interrupt number 2, which is called non-maskable interrupt. And this one also cannot be disabled. So remember I said in this table, most interrupts are synchronous, but this NMI, non-maskable interrupt, is actually asynchronous. So again, it's kind of like a backdoor. Interrupt says, okay, there are some super critical cases in which you have to handle an interrupt because otherwise, the system will not make it forward. And those typical are, the reasons for NMIs are like real critical errors, like on a bus or on a memory, like when you write into physical memory, right? And the hardware will deliver this error as a non-maskable interrupt. Some debugging cases where you say, look, I'm trying to debug the case inside my kernel. I'm already debugging an interrupt handler, so interrupts are disabled, and yet something else is happening. And at this point, you also want to use a non-maskable interrupt to yet like pass the control to the system, right? And you will see like probably it's not as important to know all the cases, but just have this intuition that non-maskable interrupts will not be disabled. However, the first non-maskable interrupt disables the future non-maskable interrupt, right? So you will get only one, and then until you IRAT from it, the next one will not be delivered. Yeah, so x86 doesn't handle non-maskable interrupts. They simplify everything. Linux does, right? So you will see it in real life sometimes. Question. Right, so good question. So the hardware has queuing mechanisms. So if the device says like, when I say raises, so the device uses some hardware logic to say, like, I want an interrupt. And that signal will be staying there on the CPU while the interrupts are disabled. The moment you re-enable them, you will get the interrupt. So the hardware does some kind of queuing. And there are multiple interrupts. I don't remember exactly what happens to the priorities. Like if you have an interrupt, and can you say that another one is a higher priority? I don't remember which one will be delivered first. Yeah, so you have to read on that. So I don't remember. But naturally, like, yeah, you don't lose interrupts. Okay, cool. So we got the ideas, and some of them interrupts cannot be disabled. That's my like slide which explains non-maskable interrupts and cases. But cool. So now it's time to take a look at how we can actually implement an interrupt handler. I said that it's regular, again, combination of C and assembly code. So again, most of the interrupt handler you can compile from C, but maybe the very first instructions where you have to save the state will have to be done in assembly. And this is what x86 is doing. So x86 uses this function. Remember, it's our beautiful main. So I also show it here. We discuss these two. Like there is a couple of like functions which initialize advanced programmable interrupt controllers, APIC. It's just negotiation with the hardware that, okay, how the interrupts will be delivered. I don't want to go into the details. You can read later, right? But okay, they initialize something, but this function, TV init, it's a trap vector initialization. TV stands for trap vector, initializes the interrupt descriptor table, IDT, right? Okay, cool. So this is literally the code of this function. So it says, okay, look, initially, I have a global variable IDT. I will initialize all the entries from 0 to 255 with the following code. Say, okay, I will put an address of a vector, so it will have an array of interrupts, and says I will write this into the interrupt descriptor table. And one IDT entry is special. This is for handling syscall. And the special thing here is the following. Two things, right? So, and we talked about it before. So first of all, the syscall will not disable the interrupts, right? And this is controlled by this flag. So it says, well, all interrupts, the moment you receive the interrupt, will disable the future interrupts. But syscall is special because it's kind of like a function. So like, let's run with interrupts enabled, right? And so this one says, okay, please do not disable the interrupts on the syscall. And the second thing is the following, this address, this field. So all the interrupts are initialized with descriptor privilege level 0. It means that if you do something like int 14 in your code, which means that you try to invoke a page fault interrupt, the hardware will not allow you because you can only invoke the interrupt which is configured with the privilege which you can access. And so if you run at privilege level 3, obviously you cannot access 0. You can only access level 3, right? And this is why for the syscall, we put this field to 3, meaning that you really can invoke int x40. Then this is 40, x40 for syscall, right? So that's the difference between syscall is special, right? Agree? So, okay, cool. So we understand it. And so we are inside this function TV init. And here I have this in, like, again, explanation of why we do not allow user to invoke int 14, for example, or any other interrupt. And again, when I say descriptor privilege level, remember that every entry in the interrupt descriptor table is this. This controls the privilege level. So if it's set to 0, only the kernel can do int, for example, 14. But kernel will never do it because it doesn't make sense, right? So, however, of course, if you're doing a move instruction running at current privilege level 3, right? And you're moving, like accessing a memory which triggers a page fault, of course, this interrupt will be delivered because it's triggered by the hardware itself, right? While walking the page table, hardware realizes that, okay, the page is not mapped, it passes control to the, triggers the interrupt, the page fault interrupt, right? But the hardware, the user cannot explicitly invoke int 14 page fault, right?
Is there a reason for x32? Or is that just some
random? Oh, no, it's timer.
Oh, that's the timer interrupt?
Just to illustrate the argument that user cannot pretend that the timer interrupt happened or a page fault.
To like enforce a.
Yeah, to force, yeah, to force the transition.
Can it only do x40?
Yeah, correct. And everything else will trigger a protection violation exception. Okay, good. Okay, good. So that's why all entries will be configured with 0 here, DPL, and 1 for syscall will be configured with 3, right? Allowing the user to invoke it.
What's 14?
What's 14?
Yeah.
If I'm not wrong, 14 is a page fault. I can be wrong. 14 is a page fault.
Oh.
My short memory works, but will not work for too long. So, okay, cool. So 14 is there. So that's why we do this trick. Okay, we got this, a couple of slides on that, and this explanation that syscall is a trap. Intel was trying to introduce a lot of terminology. They said that trap is an interrupt which does not disable further interrupts, right? And it's controlled by this flag. Again, there's only one like that. Okay, question.
Trap was instruct, like part of the items.
No. I mean, first of all, I was never very good on terminology, right? So, but I think Intel has 3 words, at least 3. So they have interrupt. That's what I remember. They have exception. And they also have trap. In real life, like modern life, you will almost never say trap. You will be saying only interrupts for asynchronous interrupts and exceptions for synchronous interrupts. But I guess they also have a designation of trap, which is a synchronous, or maybe even a synchronous interrupt, which does not disable further interrupts. But like I haven't read the Intel manual recently, so I don't remember, but that's about. Okay, cool. So how is the interrupt processed, right? So again, let's use an example of a timer, right? So vector 32, we remember this figure, right? So interrupt vector pushes, like forces the transition through the interrupt descriptor table. Interrupt descriptor table might choose a different code segment, which will choose an entry in the global descriptor table, switching your privilege level. It also needs a stack to process an interrupt. So the stack is pointed by the TSS, right? So TSS will choose the location of a stack, and the hardware pushes this 5 and sometimes 6 if there is an error code values on the kernel stack, and that's done obviously because we don't trust the user value of the stack, right? And at this point, we start executing some code in the kernel, like x86 uses the name vector 32, and this is specifically this field of the interrupt descriptor table, the entry in the interrupt table, which points to the beginning of this vector. If I ask you a question, is it a physical or a virtual address? Good question. So tell me. Just to make it clear, any guesses? Physical, okay, so we have a couple of votes for physical. What will be wrong about physical address? It's doable, but I kind of argue that it's not the best design choice for the hardware.
You can't really access the instructions would try to take note to a physical address, but really be going to those.
Correct. So if you say that this is a physical address, you somehow immediately have to switch the CPU into execution of physical addresses because you start fetching instruction from this address, right? So it's a little cumbersome. So that's why they made a smart design choice and left it virtual. I think if you haven't enabled segmentation and paging, that will be a physical address. So I think you can enable interrupt handling on purely 16-bit no segmentation, no paging. Then it will be physical address because everything is physical still, right? But in this case, since we switched to virtual addresses, that will be a virtual address. So it will go through a page table, right? So like instruction pointer will be like following the same kind of translation as everything else, right?
And this would be part of the motivation, probably not needed.
In the same virtual address location? No, the kernel can be. Huh? No, virtualization of memory allows you to put those handlers anywhere. They don't have to be continuous. They don't have to. Okay, good question. Is the IDT per process? I think, and from the example of the source code which we just saw, it looks that IDT is 1 per system. That's a great question. I keep forgetting to come to it, but since you're on it. Okay, I claim that IDT is single global for the entire system, right? If I ask you a question, again, very good question for the quiz at the end of the week, so I should somehow remember it. Which data structures, which are here on the slide, have to be per process or per something else, let's say per CPU, per physical CPU? It's a little tricky.
Basically, the PBT would be per process. What else?
It's a little hard to answer. So maybe let's wait for it, but the GDT will be, I say GDT will be per physical CPU and TSS will be per process. And a page table, of course, will be per process. And the reason for that is that every time the process is running, it will need a kernel stack, meaning that because you will need a way to handle a syscall, for example, you need the space to save these registers. And then you may want to context switch to another process. So which means that if you want this stack, then this field and this TSS have to be reloaded every time. Every time you switch to a new process. So I take it back. This will be per physical CPU. And every time you switch to a new process, you will just change this field, right? And since the system will be running on multiple physical CPUs, let's say 2, you will be able to handle interrupts concurrently on both of them, right? So you will have an own version of a TSS and this field points to the TSS. So you will have own versions per CPU versions of global descriptor table and TSS, right? We'll come back to it. So maybe it's too early to explain this because it's too cumbersome, but we have to essentially understand how the system runs or boots into multiple CPUs and what's going on. But I will come back to it.
I mean, the multiple CPU could also share the GPU.
No, that's my point. And because this field is fixed. So on a single physical CPU, this is okay, but every time you switch to a process, you will change this field. Okay, I take it back. We have to spend 20 minutes to explain it. So I'll come back to it. So just heads up, and at some point come back to this slide.
What is TSS?
Task state segment. And I don't know if you were here last time, it's a giant data structure, but only 2 fields are used. And one field is to choose the stack segment from the global descriptor table. That's why there is an error here. And a second field is to choose the stack in a kernel. So there is a second ESP pointer, right? And everything else is not used. Okay, good. Okay, so what's inside this vector 32? That's what we want to talk about today. So again, in x86, and it's a decent design choice, vector 32 is assembly code. It pushes a dummy error code because the timer interrupt, the hardware itself does not push the error code because timer comes without any error code. If you don't add this instruction, you will come up with a different stack layout for some interrupts, meaning that for vector 32, only 5 things will be pushed by the hardware, right? But imagine we have an exception which pushes an error code, then this error code is an extra field, and it will have 6 elements on the stack, right? Later on, you will have to distinguish between the stack layout because you want to access fields saved on the stack. So they make life a little bit simpler. And instead of saying, I will dynamically decide whether I pushed 5 or 6 field, I will push an extra field error code here. It will be dummy, it will be 0, but it changes it to 6, which makes the layout of the stack always the same, right? So a smart engineering choice, right? To avoid thinking about it later. Then it pushes the number 32 on a stack itself. And this number 32 will later on, when you switch to C code, for example, will allow you to know which interrupt you're currently processing, right? Because vector 32 is special. You know that you're in entry 32 of a page table, but then the moment later you jump to a generic all traps code, which handles any interrupt, right? And this number 32 leaves the information saying, okay, we are actually handling the timer interrupt number 32. Clear? Right? Good. So now we jump to all traps. When we jumped, or before we jumped, the kernel stack looks exactly like this. So the hardware pushed these 5 fields. We pushed error code 0, and we pushed interrupt number 32 on the stack, right? That's the layout of the stack, right? Why is it important? Later on, this data structure on a stack will be called a trap frame. And this trap frame is we'll use a C data structure, but for example, to see which interrupt number we are using, there will be something like trap frame. I think it's field N, which will be mapped to this. Oh, sorry, not to 0, but to 32, right? And all the registers will be saved on the stack as well. So if you say, okay, what was the user register at the moment when interrupt happened? So you will be doing something like trap frame EAP field, which will read this value. And that's the value of the user register saved by the interrupt handler, right? By the hardware too. Okay, good. Okay, cool. So then all traps, if I ask you a question, what is it? What needs to be done? Like, what do you think should be an outline for handling an interrupt? What's your goal here? You kind of can guess from the code, but Like if I ask you in English, what will be the plan? Because it's easier. Implementation is not super interesting. Like I mean, it's interesting, but it's not nothing super unusual. But what is the high level outline for the interrupt handling? I showed you the first, like whatever, 3 instructions, 2 pushes, 1 jump, right? Which did what? Tell me in human words.
It looks like it's saving the rest of the context from which it's called, calls the threat that is specific to the vector 32.
Correct. So at a high level, what you have to do on the interrupt handler pass is to save the state, because you may never come back to this process. You may come back later. Because it's a timer interrupt, you're going to do a context switch to another process. So later on, when you come back, you have to save all the registers, to restore all the registers, right? So at a high level, that's the reason why it's written in assembly, because you very carefully control what instructions are executing, right? And on this slide, it's 2 pushes. They only touch stack, but they don't touch the registers, right? So the registers are still intact, which means that those are the values which user code put in those registers, right? So you will be able to save them and restore them. So the goal is to save those registers, right? And so the code essentially first saves the segment registers, because who knows what the user was doing. They were maybe they were changing DS, ES, FS, we don't know. And there is a special instruction, push all, which x86 is using, which is not strictly necessary, but it's instruction which semantically is equivalent to pushing all the registers. The first saving ESP in a temporary CPU register, then pushing it at a high level, just push all the registers on a stack. You can really just do one by one. There is no harm in that. So just whatever. x86 chose to do this, right? And so after you push all, you make sure that you're running that your DS and ES segments are initialized to kernel data. SS is already initialized from the TSS. Remember, the TSS chose this value for us. And the code segment was initialized from IDT, because when you switch from user to kernel, you automatically choose the CS value, which was written in the interrupt descriptor table, right? And after that, you say, look, my goal is to switch to C, because at this point, I don't need to deal with assembly. You're going to call a C function trap, right? Obviously, you need to somehow pass this state. So essentially, remember that you were saving everything on a stack here, right? So let me clear everything. So you were saving all these additional registers on the stack, right? EAX, EBX, and so on, right? You want to go into C. Let's call your C function is called trap. How will you pass this information to C? What's your trick? You're gonna do what? Exactly. So remember that the calling convention, so if you say, look, I have a C structure, which we call a trap frame. And if the function takes this one argument as a pointer to the trap frame, the calling convention is that this argument should show up on the stack, right? Agree? As an argument to a function. Yeah. But since you want to pass the pointer to the trap frame data structure, and trap frame data structure is allocated on itself, on the stack itself, right? So the beginning of the trap frame was ESP right here, right? If we push this ESP on a stack, we exactly get what we want. There will be a pointer to this stack itself, right? Is that clear? So if it wouldn't be on a stack, and it's totally fine, so you don't really have to save everything on a stack. If you can locate a global, like you say, like I know where this global value for the context somewhere in a data section, go ahead and instead of pushes, use like moves here, but they do it on a stack, right? But this is the trick. So they push the value of the current ESP following the calling convention. The resulting layout of the stack is specifically like this. You have a pointer at the very top of the stack, pointer to the rest of the stack, and this data structure is called trap frame. And so now you're ready to go into C. So essentially you say, look, well, that's my C structure, C function. It takes one pointer as an argument, right? And a pointer is passed on the stack since we essentially following the calling convention. Good, any questions?
What's 32 and 64?
What's 32? Again, where is it?
Interrupt 32, and then you also have interrupt 64. What's this number?
Where do you
Then you
see?
have the other ones in the right. Right. Interrupt 32. And you also have another one interrupt 64.
Where's 64?
The green.
So this is the backtrace of which functions were called by the hardware, right? So just to make sure that you understand where you are in a kernel. So int32 was triggered by the hardware. You landed on the vector 32 label. Vector 32 label did the jump to all traps. It was a jump, it wasn't a call. And all traps did a call of trap function, right? That's what I tried to explain here.
Do all interrupts end up at all?
Yeah. And again, like I wasn't specific about it, but yes, the only different thing for the interrupt is this vector 32 assembly piece.
Do all interrupts also end up at that?
Yeah. Yeah, and it makes sense. So you can design the kernel differently, but it makes sense to kind of like generalize. And inside the trap function, so I skip a couple of lines here, right? So I skip some here, but there will be a switch case. And remember, I said that we will be using this trap number, which we pushed on a stack to distinguish between them. And this case, which I like illustrating here, is actually a timer interrupt. So it's a first IRQ and a timer interrupt. That's how they define it, but it really evaluates to 32, right? And then you start handling the timer interrupt. And this is the code which specifically handles the timer interrupt. So it increments the global time clock ticks. And later on, this is the second part of handling this code. It says, okay, if there is a process which is running currently and the timer interrupt has arrived, then yield making sure that you're going to switch to another process, which kind of logically, I kept saying that timer interrupt triggers a switch from one process to another, and this is how it's encoded, right? And later on, we will explain how the yield works. Question.
I just want to ask a question. So vector is called the only thing it's actually doing is depending on which interrupt it is input, either one value or two values.
Correct. Right. That's
Otherwise, that would have
no, this is the entire code of the vector 32.
But it could be something else for different.
Yeah, for example, for vector 16, I don't remember which exceptions push error code. So let's say for a second that page fault pushes an error code.
Yeah.
Then since the error code is already pushed by the hardware, there will be no line like this. There will be only two lines, push 14 on a stack and jump to all traps immediately.
So all the vectors will be at a 3 line.
Correct. And they are in fact automatically generated from a script because you don't have to write them, but you can if you like. Okay. Another question.
I remember at the beginning you said when we do the interrupt handler, we need to consider two cases. One case is the switching between the user level and kernel level, and same cases we don't need to switch. For example, they are both in the kernel level. So that happens before this phase, right? This is actually
Good question. So I appreciate it. Sorry, I wasn't clear about it. No, it's a single pass. At the level of the code, you don't have to think about it. Because if there is no switch in privilege level, simply there will be some other stuff on the stack already. So my illustration here starts from a clean kernel stack. But if you already were running inside a syscall, so first the syscall will push something on a stack in exactly the same thing, right? We'll go into the processing of a syscall code, right? So maybe more call functions, more stack growth, right? You're already in the kernel at privilege level 0, but syscall did not disable further interrupts. So the timer arrives and says, okay, look, I will preempt execution of a syscall. and we will handle the execution of a timer interrupt. So this stack will be just right under this original, like on the same kernel stack, somewhere over here, instead of 5 fields, it will only say 3 fields, right? So it will not change the code. No, it will not change the stack, right? So these 2 fields will be gone, right? Okay. Good question, however. Good question is, how will you deal with a different stack layout? Because the 2 fields are missing, right? Because the hardware did not push these 2, SS and ESP. It's a great question, and I don't know the answer. I used to know, and I don't remember anymore. But did you get the gist of it, right? So clearly the stack will be slightly different. How the code will deal with this. It's a good kind of investigation, little investigation in the x86 code. I remember doing it in the past, but I don't remember the exact answer right now. So I'll come back to it in that answer. But at least I answer first half of your question: what happens if you're already running inside the syscall, right?
I'm just guessing, but do you think the padding of the structure would take to NTP?
But we don't pad anything, so right, so
Like it already from the structure.
no, like it looks like, no, I have to, let's take a look, but the padding will not solve the problem, because some fields which will be allocated on the stack before can be interpreted as SS and ESP. My naive guess is, yeah, say again.
Like if the entire craft frame is aligned, then do you think that would be an implicit?
The hardware will not align. I think it will just go to the, remember I was showing it that without the interrupt transition, literally the stack will be, sorry, where's my pointer here? I almost hit the right button, but I didn't. I lost the mouse pointer. Just let me show you quickly.
Oh, see what you're talking about, not 64.
Yeah. Right. So on this slide, this is what the hardware will push, only 3 values plus an error code. And it will not align anything. I think they actually changed it, and I have to double check, but I think when they moved from 32-bit to 64-bit architecture, they said that this is so cumbersome that we will always push 2 extra values or something like that. But let me double check. So I don't want to say this. Okay, so we get this. So we are inside the vector, we're inside the trap. We kind of see logically that it looks like a real context switch, right? So on a timer interrupt, right? So any questions about what was done here?
Just as a brief refresher, vector 32 is pointing to by the interrupt descriptor table, right?
Correct. So essentially, I show it green, but really it's a pointer from the interrupt descriptor table. And it's this handler, like virtual address, which points to the vector 32. And specifically, I will show you how this table is initialized. Okay, just wanted to quickly handle what happens on the exit from the interrupt, right? So we entered the call trap right here. That was the old traps, right? So obviously, when we return from this C function, we will end up here, right? Since we pushed 1 value on the stack, we deallocate it, right? By, by adding 4 bytes to the stack pointer. And after that, we start returning. So we just fall through here to the trap rat label, pretty much reverse sequence. We pop all, essentially this instruction, which is symmetrical to push all, it restores all general registers. We pop all the segment registers because our stack layout matches what we constructed when we were entering this old trap handler. At this point, we deallocate 2 values which we pushed on a stack in the vector 32. So it's a trap number and the error code, right? We say only 5 values have to be on the stack at this point. And at this point, we invoke a special hardware instruction, IRAT, return from the interrupt, which is similar to return to the rat instruction, but it picks, instead of picking one return address from the stack, it actually picks those 5 values and restores them. So it will be a stack segment, stack pointer, will be code segment, user code pointer, and the E flags register, right? So 5 things. And we're back to user at this point, right? So the next instruction after IRAT, if we entered from user, will go back to user. If we entered from 0, it will actually go back to 0, like if we were in a kernel already. This is clear? Okay, so this is a complete pass. So that's like, again, just another illustration how the stack looked. We X'd, restored all the register, again, wanted to come back to this one. So IRAT restores code segment, instruction pointer, E flags, stack segment, stack pointer, and we are back to where we were when timer interrupt hit us, right? So, okay, cool. I will stop here because it's probably too late to start the system calls, but we will essentially handle the system calls next time. We'll finish them and move on. But yeah, with system calls, the tricky part is to figure out how to sanitize the arguments to make sure that user doesn't try to confuse or exploit the kernel. Okay, thank you. My office hours are today, so I will see you then today or Thursday.